next thing is just for me to say how honored I am to introduce to you Professor Rashed today, and I really mean it this time because with Professor Rashed we actually have here someone who has really changed the perception of the field with his work. Professor Rashed has been teaching for many years at Paris 7, but also has had positions as a researcher and visiting professor in the US, Europe, and the Middle East. And his list of publication is impressive. And we could spend the next couple of hours just reading the titles of those publications, but rather than doing that, I will just tell you that he has published around 40 books and more than 100 scholarly papers, mostly but not only on Arabic science, and with a specific focus on the exact sciences, mathematics and optics being one of his main concerns. And in this area, I would say Professor Rashed has not just put forward new interpretations and new ways of looking at existing materials, but his work has been also crucial in terms of providing the scientific community worldwide with a wealth of new materials that actually were not available before. So there is all work of authentication of manuscripts, publication, translation, providing commentaries for these texts that Professor Rashed has been carrying out for years now. I just want to mention a couple of works that I think are landmarks, like the Encyclopedia for the History of Arabic Sciences in 3 volumes, and 4 volumes of a study on infinitesimal techniques as used and deployed by Arabic mathematicians between the 9th and the 11th century. And I'll just stop at these 2 major works, because as I said, otherwise I could go on for quite a bit. So I'm very pleased to hand it on to Professor Rashed. Thank you.
Thank you so much. Yeah. Dear colleagues, please allow me to begin by thanking Professors Katharina Carson and Massimo Mazzotti for the opportunity to address you today and for their invitation. I am really very pleased to be here for many reasons. One of these reasons that I found here my old colleague, I mean in the time, Roger Han, and it was really a pleasure to see him again and to discuss with him, because we didn't meet since some years. Good. I would like, before my talk, to mention some names and some titles not familiar for everyone. Also, I would like to remind the definition of some things before. The names and the titles are the following. That is, you see, or you need focus? Yes. The first one is Khayyâm. He is a mathematician. The date is wrong because he could not be born after his death. It's impossible. Then the date, 1084, 1131. He worked on 3 main subjects. The first one, as you will see, algebraic geometry. The second one is the theory of proportion. That is the first contribution to the theory of proportion with continuous fractions. And this work was known by Wallis later on. The third book is about the 5th postulate, and this book was also known by Zachary and Wallis later on. That is the 3 main books. And 3 main contributions. There is other contributions, but I insist on that because I will speak especially about algebraic geometry. The second person, I suppose you know him, that is our friend Descartes, and I will speak only about his geometry. As you know, it is 1637. and it is a part of the discourse on the method. Bon, Viviani, Torricelli, that is, I will mention their names for their contribution also, and especially Descartes, the Brouillon project. As you know, it is the first contribution, the first serious contribution in projective geometry. There was before, as I will say later, a work on projective geometry, but it's the first time that the notion of infinite point and the infinite line are used. I will mention also this man, Couhy, mid-10th century, for 2 or 3 reasons. The first reason is that he generalized, as I will mention later, the criteria of admissible construction in geometry. The second thing, he is the first to formulate, to elaborate a theory, projective geometry of the sphere, only the sphere. And the third thing, that he invented a universal compass to draw all the figures, all the second degree curves. This man, Sharafuddin Tusi, I will call him Tusi. He is not the famous Tusi who worked in astronomy and so on. This man is an algebraist, and he pushed algebraic geometry towards analytical method, as I will mention later on. But I wanted to pronounce the name because I suppose that some of you are not familiar with these barbarian names. Who else? Bombelli, perhaps you know him. Fibonacci, perhaps I will not speak about him. In any case, that is the most names. The second thing that is from this direction. Just to remind you, because you have not that all the time, what is a cycloid. Because of the importance of this curve in the 17th century, you have the definition, the analytical definition. We don't need to know more about it. That is, what else? No. Now I come to my subject. In this talk, I will discuss mainly the question of mathematical modernity, starting from Descartes and his contemporaries. Fermat in particular, if I have time. If not, I will not speak about Fermat. For me, Fermat is more important, but in any case. By mathematical modernity, I understand the modern beginnings of mathematics. In particular, toward the end of the first half of the 17th century in Western Europe. The whole question is to know where these modern beginnings are exactly and what is their relationship with the heritage which was theirs. That is, then it is a historical question which I will deal with, and at the same time it is a methodological question, how to discuss this question of the beginning of the modern beginning of mathematics. Can I sit down a little? It still remains, and that is important, to distinguish between mathematical novelty and mathematical modernity. In the case of mathematical modernity, it is not enough anymore that the result, theorem or proposition whatsoever, is new. It must, moreover, be that of a research program itself new. If we agree, however, in less than 1 decade, 10 years, between 1630 and 1640, one sees declaring several mathematical programs. In 1634, Roberval engaged research on a new transcendent curve, the cycloid. Descartes and Fermat will not be long before joining him. And himself, 4 years later, in 1638, always followed by Descartes and Fermat, find the surface of an arc of cycloid, The same year, he places the tangent at a cycloid by a kinematic method. Viviani and Torricelli will find it independently a year later. This research on the transcendent curve, the most famous transcendent curve in the 17th century, inaugurates a geometrical analysis on transcendent functions, analysis promised to the future that one knows. That happened before. During the same decade, Descartes and Fermat had given methods to find the slope of the tangent at a point of x coordinate of a given algebraic curve. In 1639, de Beaune required, on the contrary, a method making it possible to find the curve starting from a known algebraic relation between the x coordinate of the point and the slope of the tangent in this point. Thus is posed the problem, the famous problem, of the reverse tangent, and inaugurated as a result a new research in differential geometry. Always during this decade, and precisely in 1639, again, Desargues completes his famous Brouillon project, which enriches research in projective geometry. It is still during this year, in 1640, that Fermat invents the method of infinite descent, thus renewing the theory of number. 3 years before, in 1637, Descartes' geometry has already appeared in French. The translation of Van Schooten is later on, the Latin translation. Such a multiplicity of fundamental works in such a short amount of time is sufficiently singular phenomenon in the history to deserve to be studied as such. But it is also important to locate each one with rigor in the history of mathematics. I limit myself here, for obvious reasons, to the principal domain studied by Descartes, that means algebraic geometry. I don't say analytical for very special reasons. The question is the following. Is Descartes' geometry the effect of a new program research, and does it comprise new results? If so, in what sense? This question leads us, whether we like or not, to the history of geometry and the algebra before Descartes. They also lead us to consider the evolution of his own thought between 1619, especially, 1619 he was 23 years old, and 1637, because that's in this period that discovery will happen. This is a habit to focus the representation of this history at two times. Now, if you look to the history of algebraic geometry, as it is done by very serious people, for instance, my late friend Michael Mahoney, or in his book about Fermat, The Royal Road, or by a famous mathematician, Jean Dieudonné, in his book on algebraic geometry, and many, many other. I also mentioned two. The history of algebraic geometry is done in the following way. They begin by the conics of Apollonius, and then they jump on to the late 16th century to Vieta, and the history of algebraic geometry will be the combination of the conics of Apollonius and the algebra of Vieta. That is almost the picture which we have in the books of history of mathematics. But here I have between commas I have to mention that they, at this moment, they knew only the 4 first books of Apollonius Conics. As you know, Apollonius Conics is composed of initially 8 books. The eighth one was lost before Pappus, I mean before the 3rd century. And for the, in Greek, we have only, how you say, the Autochius version of the first 4 books only. And the 3 last books exist only in Arabic, and in the new edition of all the conics, all this has been done once more. And there is many problems. That's what I try to say only is the following, that in the 17th century, they knew only the first 4 books of the conics. The 5th book is a very important book. It is about the maxima, the lines, the straight lines, maxima and minima. And this book exists only in Arabic. It will be translated in Latin by the famous astronomer Halley late in the 17th century. But the content of it was known already at the end of the 17th century. That means after Descartes and so on. That is the general picture of algebraic geometry. Now, we know indeed that during the 10th century, I come back now to the 10th century, several mathematicians carried out the translation in terms of algebra, certain geometrical problems, plane as well as solid. Among these mathematicians, some thought of solving one or the other of cubic equations obtained by the intersection of 2 conical curves. But 1/2 century later had to be waited so that Khayyâm, as 1048, 1131, gives himself the theoretical means, that means unity of measure, dimension, geometrical calculation, etc., to work out a general solution of 3rd degree and biquadratic equation with the help of geometry. In fact, Khayyâm gave himself the theoretical means of a double translation to bring back the geometrical solid problems to algebraic equations, to solve the irreducible algebraic equations of the 3rd and the 4th degrees by the intersection of 2 conical curves. That is this, may I say, dialectical movement, or this double movement. If one wants to express this double translation by a formula, we could say that the birth certificate of algebraic geometry is at the meeting point of algebra of polynomials, which has been invented and developed before, 2 centuries before Khayyâm, and research on conic sections, undertaken since the middle of the 9th century with the help of Apollonius Conic. Not only Apollonius Conics, but there will be a research on the conics which will be fundamental to the new conception of this kind of mathematics. This convergence will take place in the 10th century for one or the other of geometrical problems randomly, but systematized by Khayyâm. Let us see, have a look. This is the summary of what Khayyâm has done. The equation of the 1st and 2nd degree, this is not a problem. It begins with the 3rd degree and later on the 4th. That, as you see, every equation, it chooses 2 cubics, 2 quadratics. For instance, for the first, the 13 one, it is a circle and a parabola. For the 14 one, it is parabola and hyperbola, and so on, and so on, and so on. That is for the polynomial of free term. For polynomial equations, he will do the same thing as you will see. That is circuit hyperbola, hyperbola, and hyperbola, etc. All the problem is thus to understand the reasons of this meeting, of the meeting of algebra and the research on the conics. Why? And why it occurred at this time and in this place. For that, it is necessary to start by recalling that it was done in relation to the constitution and evolution of two groups of disciplines throughout the 2 centuries which preceded Khayyâm. The first group of disciplines is that of polynomial algebra and the theory of algebraic equations. The second group that everybody knows more or less. The second group is composed of 2 geometrical chapters. The first one is relating to geometrical constructions by intersection of conics. To construct geometrical construction with the help of conics. It is not anymore as in the old geometry, as in the Greek geometry, that of Autocrates, for instance, about isolated problems emerging in a sporadic way and solved by the intersection of curves, conics or others. As you know, in the Greek geometry, there is construction, but the only construction by conic seriously was done by Autocrates in the 6th century. But before, there was construction using any curve, especially some transcendental curves, other not transcendental, but there was no a theory of the a theory of curves by which it will be this kind of problem, 3rd degree or 4th degree, will be constructed. But now there is a method to explore the field of the geometrical problem, solids, in grand majority, or biquadratic, with exception of all the others. There will no more use of transcendental curves to construct geometrical problems. They isolated, in a way, the type of curves used to this construction. Within the framework of this new chapter, certain mathematicians, and there is one which I didn't mention, but I have to mention, Ibn al-Haytham. He died after 1040. He is the man who worked in optics, in mathematics, in everything. I see this man generally with curves, another problem, the existence of solution and their number. And that is a very important question. Why? In the Greek geometry, there is the discussion of number of solutions. You have just to look, for instance, to the 4th book of the Conics of Apollonius. There is a study of the number of solutions of this kind of problem. But the problem of existence was not a main problem in Greek geometry. There is a problem of construction, but not separated from the problem, but separated, not, there is existence and construction was almost the same problem. But the problem of existence as such will be raised, and raised very seriously, especially with the algebraist method and by the method of analysis and definition. In any case, cultivated by the mathematician as of the middle of the 9th century, this new chapter became a field of active research with those of the second half of the 10th century, offering to the algebraist methods and the techniques, and especially a new criterion of admissibility. As you know, in Greek mathematics, only construction by rule and the compass are admissible. From now on, construction using conic section is an acceptable construction in geometry as well as with the rule and the compass. This is undoubtedly a quantum leap. Moreover, this same mathematician who during construction proceeded by geometrical transformation, that means similarity, translation, homotopy, affinity, and so on. And that is quite different, and these techniques, excuse me, which some will be borrowed by the algebraists, endeavor to introduce the movement into the geometrical statements and demonstration. It is not here, it is not question here of kinematic movement, but of geometrical movement. That means disregarding the time employed to achieve. Here I would like to mention only this remark. As you know, in Greek geometry, and especially Euclidean geometry, Apollonius is a little different. In Greek geometry, and especially in Euclidean geometry, it is a geometry of a figure. It is not a geometry of the relations between two figures. Then all the problem of transformation is not really raised. It will be in a way or in a way or other touched by Apollonius in the 6th and the 7th book of Descartes. But and that the mathematician of the 9th and 10th century will develop this kind of geometry of transformation, that not geometry of a figure, but geometry of the relations between figures. And that will be important to our side. But as the problem of existence is raised, then we need to have a continuous drawing of the curve. If not, we cannot speak of existence. If you want to prove that two curves has to cut at a certain point, and if you give equations of that, this point, the projection of this point on the axis will give you one of the rules. But you have to prove that you don't jump. I mean that really these curves are continuous and they will cut at this point exactly. And that's it, a new problem in geometry which will be raised. Then there are two things to do. One, the first one is to introduce the motion in geometry that was forbidden in the Euclidean and the Aristotelian legacy. There is no motion in geometry. Even in the Platonian, it is no motion. Now you have, there is motion in the 13th book, for instance, in Euclid, but it is by, how you say, by counterband. Yeah, I mean, not seriously. I mean, introduced by counterband. What do you say counterband in English? In any case, there was no, I mean, it is outside the job. Even if you use it, it has no legitimate position in job. Now, the people of the 10th century are obliged now to raise this question, this continuous movement, that means displacement, rotation, and so on, is carried out using one or the other instruments and always reproducible in exact way. If you want to speak about it, you have to reproduce it in the same way and in the exact way. And at this moment, they will invent what they call the universal compass or the perfect compass. I will come again to that. That is the first chapter. The second chapter of the second group of disciplines is akin to the theoretical and the practical study of the procedures to reproduce the movement, and thus to draw the conical curve. Indeed, their drawing by points was already an object of research for a long time. We know how to do it. That accelerated during the 10th century. But it is only at the end of this century that arises the problem of continuous drawing of all the curves used in algebra. Optics, in algebra, in optics, in the manufacture of the mirrors, lenses, astrolabes, sundials, and all this kind of thing. Admittedly, we know that the ellipse was drawn before by the method known of the Gardner, to pick the point to be around. That is Anthemius Australis in the 6th century. But it is only at the end of the 10th century that the problem of the continuous drawing was raised for itself, and in relation to the whole class of curves, of quadratic curves, first and second degree, and of the invention of instruments necessary to its realization. However, if the mathematicians of the time began such a research, it is because, among other reasons, they had to make sure of the continuity of the curve. As I said, this last concept was essential indeed from now on during the demonstration of the existence of the points of intersection of the curves, which was necessary to the construction in geometry and with the solution by the algebraists of the cubic and the biquadratic equation. But this research on the continuous drawing is not only theoretical, it is also necessary to design and work out new instruments, and I mentioned one of them. There are many instruments for that, but I mentioned the perfect compass. However, these studies were not long in leading to the main issue of the classification of curves. And now we will take a really very important question and write it directly connected with Descartes, as you will see. Now they have to classify according to the type and number of movements which intervene in their drawing. If you will draw the curve by one movement, by two movements, which kind of movement, or this kind of problem. Thus, Khayyâm, the man whom I mentioned, the first mathematician who composed a treatise on the perfect compass, distinguishes the curves drawn by this compass, straight line, circle, the three conics, and so on, and calls them measurable curves. The measurable curves, he used the word measurable curve. That means the likely ones to be studied by the theory of proportion. In this sense, they are called measurable. It is thus about plane curves generated by only one continuous motion. Continuous motion, you will have this curve. Possibly by more than one movement, but of similar nature, and to which the theory of proportions is applied, which remain exact whatever the characterization of the curve. You can characterize it by the Saint Thomas, as in the Greek mathematics, by focus and the directrix, by equation as well. One younger contemporary of this Khayyâm also classifies curves according to the type and the number of movements, measurable ones, like previously, and which are geometrical, so we call them geometrical, those generated by two different continuous motions, which would either be measurable nor geometrical, but according to him, only mechanical, are, however, regular and odd. That is, for instance, as the cylindrical helix. It is generated by two movements, rotation and translation, and these two movements produce this, but it is not geometrical, it is mechanical. In his definition, we shall see what it means later. This distinction between the classes of curves is so much important for the history of algebraic geometry that we shall see with Descartes what it means. Then, I tried to show that it is during the 10th century with mathematicians like Coury that from now on new requirements set the standard. A real proof of existence should be given when it is necessary, and the processes of construction should be based on solid geometrical basis. Thus, the perfect compass of Coury, designed to draw conics, are not unspecified instruments, but are themselves worked out using the conic theory, which they incarnate. The mathematicians thus limited themselves, and that is the first limitation, limited themselves to the only curves whose they had the means of establishing the existence and to proceed with construction. But shortly and clearly, it is thanks to this same requirement that the mathematician could distinguish the class of plane curves of the first 2 degrees and were diverted from an active study of mechanical curves. There are no studies, real studies of mechanical curves. All was concentrated now on this class of curves which had been distinguished. That is the first limitation. The second limitation of mathematical knowledge of that time is inherent in this same class of plane curves. Why indeed, once defined the class of measurable curves, the mathematicians stopped to the 2 first degrees, while they had encountered solid and supersolid or shear solid problems. This is, for instance, if you place two let us say 2 segments. Let us say, if you place 4 segments between 2 segments, so that the 6 will be in continuous proportion, that leads you to a 5th degree equation. But they knew that. They knew more than that. My question is, why they limited themselves to this first degree? This is the 3rd or the 4th first degree. This is an avoidable question, especially since Coury generalized a theory of application of the areas to the solids. That is to say, that nobody ever tried to draw a cubic curve, and even in the first half of the 17th century. Somebody tried to trace a cubic curve. One needed for that the definition of any plane curve by its equation. In other words, the construction of a new chapter where the curves are studied by their equation. It was therefore necessary to await the end of the 17th century at least for this to be realized, not before. In any case, the distinction between classes of curves obviously did not. I have to mention only that Khayyam's successor, Tusi, whom I mentioned before, was, however, preoccupied with the proof of existence. For that, he introduced the concept of movement to ensure the continuity of curves, defined the concept of maximum of an algebraic expression, not only of 2nd degree, it would be of the 3rd or the 4th degree. He is looking for the maximum of this algebraic expression on an interval and studies certain algebraic properties of conical curves. Thus, barely half a century after Khayyâm, he shifts toward an analytical direction of algebraic geometry of his predecessor. To do that, he finds a very curious thing. He gave, for instance, you take an algebraic, he takes, let us take a 30-degree algebraic expression, and then to determine the maximum, he gives you exactly the value of the derivative, add the cost. And then he annulates the derivative and defines the maximum. All that is done algebraically, I mean without topology, but he did it not once or many times to prove the existence of the maximum. Now, things remain largely unchanged until Descartes' geometry, to which I have to come back. I mean, between the 12th century and the first half of the 17th century, you have a lot of algebraic works, Bombelli, I mean Latin and Arabic and everywhere, but for algebraic geometry, nothing worse. I mean, I don't know things to be mentioned, a contribution of Rashed whatsoever. Then I come now to Descartes. One can show that on the one hand, la géométrie represents the completion of this Khayyâm tradition. And that on the other hand, in this achievement, Descartes found all the question of the movement, classification of curves, continuous drawing, new compasses to carry it up, thus engaging a new tradition whose extension will be the work of his successor and not himself. Let me explain a little more. One can agree to recognize in la geometry an organization around the two main axes. The first, to bring back a geometrical problem to an algebraic equation with one unknown. The second, to bring back the resolution of the equation obtained to its construction by the intersection of two geometrical curves, of which one will be a circle as far as possible. That is the two axes of la géométrie de Descartes. If one restores the evolution of Descartes' thought in relation to the first axis, that means bring back a geometrical problem to an algebraic equation with one unknown. If one restores the evolution, one notices that from 1619 and until before January 32, it means more than 13 years, date of resolution of Pappus' problem, if you want, later on. He had solved just like Khayyâm, not more, the cubic equation by intersection of points. No more than Khayyâm, there's nothing else. In 1637, in his La Géométrie, he proceeds always following the example of Khayyâm with the solution of all equations of the third and the fourth degree by intersection of two points. But he restrains himself to a parabola and a variable circle, according to the type of the question, but that is not really very important. But either Khayyâm, he does not deal for the time being with the existence of the roots. For the equations of the first, fifth, and sixth degree, in which Khayyâm is not interested, Descartes conceived a cubic parabola or parabolic conchoid, which is the curve. That is the equation of this curve. But in the presence of cubic equation, for example, Descartes, unlike his predecessor Khayyâm, was reduced to declare that it is at most solid. He could not thus either specify the nature of the irrationals which intervene in the solution. He has no idea about this irrational, what they can do, I mean, in which quadratic field they are. It is thus noted, if one sticks on the first axis, Descartes reiterates the approach of Khayyâm. He undoubtedly refines it, generalizes it, carries it out to the possible logical limits. In short, he completes it, but without really neither touching the substance nor reshaping the sense of it. What about the second axis? At the age of 20, with a somewhat modest mathematical knowledge, Descartes stated a program of his own consent, ambitious, whom he did not have yet the means of realizing. Here are the principal ideas of this program. The classification of geometrical problems thanks to the curve that can be used to solve them. 1. The classification of the curves themselves thanks to the movements by which they were drawn. 2. And finally, an unshakable faith that nothing, however, comes to justify in the heuristic value of these classifications to exhaust and prove all the question of geometry. That is absolutely marvelous. At 20, he gave his program without any justification. The underlying intention of this program is, it seems, of going beyond the conics and clearly distinguish this class of curves under the strict condition of restoring to no other unknown concept of the ancient, who they, being deprived of algebra, could not locate this cleavage between classes of curves. That means the concept available to Descartes at that time is not other than the concept of movement in the Aristotelian tradition, nothing else. In his geometry, this concept of continuous motion is certainly handled without any apparent kinematic consideration, but without being covered by the slightest algebraic dimension A. During the research undertaken in the line of this program, Descartes seems to have realized that the concept of movement alone does not suffice to entirely justify the distinction he stated in 1619. That means the distinction between geometrical curves and the mechanical curves. The difference between these two classes of curves indeed seems to refer to two mixing problems. That of the constructability of the points of the curve and that of the existence of point of intersection when the curves cut each other. These problems have been encountered by Tussi, as I mentioned before, in the 12th century. But as they were the sole conical curves, it is relatively easy to deduce from the symptoma or from the equation that the point of intersection is an element of each curve. However, Descartes did not focus anymore on the sole conics, but treated the cubics and the more generally geometrical curve. Geometrical, in the Descartes sense, as you know, is algebraic. He recognized otherwise than his predecessors the role of the equation to represent the curve. However, this equation generally allows him only the construction by points, which is sufficient only for geometrical curves. Descartes is then confronted with a symmetrical situation. While for the class of geometrical curves in the algebra, one can speak the language of equations, this is impossible for mechanical curves. It was admittedly necessary to await Leibniz and especially Jacques Bernoulli, to know that these last curves do not have an algebraic equation, that they have algebraic differential equations connecting between them not the x coordinate and y coordinate, but their differentials. Descartes was not, however, unaware of all the properties of geometrical curves must be drawn from their equation. But it is known that he never applied himself to this problem. It was necessary for that to await young Newton. Newton will do this with this. Before Descartes, the concept of equation of a curve remained very limited and hardly lent itself to the constitution of a research program. For instance, Toucy at the time of the research on the maxima, or more exactly on the existence of quantum intersection, studies certain curves within their equation. It remains that he does not clearly distinguish between polynomial equation and the curve, apart from the conics. However, it is precisely thanks to the extension of the study of curves beyond the conics, I mean with Descartes, and the distinction that he established of this class of curves that can be studied by means of algebra, that Descartes could conceive this new problem. The realization of this latter remained a pledge with the future, source of two currents, that of algebraic geometry with Kramer, Bézout, that of differential geometry with Bernoulli brothers. Now, I will skip Fermat to not complicate the things, and I will come to the conclusion. Now, as you see, among the disciplines which one calls open to represent the mathematical modernity, or the beginnings of modern mathematics, during the first half of the 17th century, if not classical modernity itself, algebraic geometry is mentioned, especially with Descartes. Precisely, however, this example of algebraic geometry is a good illustration of the complexity of this same concept of mathematical modernity. As long as mathematical activity from the 9th century in Arabic was ignored, or that one jumped in with both feet over what one could know, this concept seemed clear and being self-evident, raised no problem. The modernity was then seen at the crossroad of algebra and Apollonius concept, or more precisely, the first four books, or at the crossing of Vieta La Spécieuse and of this later books. But it is rather, we know it, a meeting between algebra and the new chapters of geometry developed from the conics that occurred 6 centuries before Descartes. Without the chapter on geometrical construction with the help of conic sections, and that on the continuous drawing, one will not be able indeed to understand the birth of algebraic geometry with Khayyâm and its transformation, the first time with Toucy. Would not mathematical modernity at the 17th century be thus just a reproduction of that which has occurred at the 11th century? By no means. Would it be, as one likes to affirm, a radical beginning? Neither. we have just shown that such an alternative to look, that such an alternative is not in fact relevant. To read Descartes' geometry, it is also necessary to look upstream towards Khayyâm and the Tusi, and downstream towards Newton, Leibniz, Kramer, Lizou, and the Bernoulli brothers. And it is like the same for Bernoulli. Only then, all these innovative books will find the place which never ceased being there. La géométrie de Descartes, for example, is by no means an absolute beginning. I'm sure that it is not. But like other fundamental works, it inaugurates a style that of a recovery, an adaptation, and a correction of the traditions which it is the inheritance. But like these works, it opened the way to other evolution in algebraic geometry and also in differential geometry. Modernity comes thus in the form of the realization of some potentialities inherited from the tradition, at the same time as it generates new potentialities for the future. But could it be otherwise? Nothing prevents, if one thinks only by ready-made concept, from supporting that continuities and discontinuities are registered in each other. But any discourse on Descartes' geometry or on the books of Fermat also is condemned to be oblique if it neglects intimate bonds which rule these works in the tradition, as well as new possible ones which are inhabited in them and whose actual realization should wait for modernity to become itself a tradition. And it is not by chance that it would. Who realized that was Newton, Leibniz, the Bernoulli, and the later on Kramer. Thank you.